Welcome back, everybody, to our next talk, which will be held by Jochen Lillich, and he will talk about dynamic infrastructure orchestration.
Hi, and welcome to my talk. My name is Jochen Lillich. On Twitter, I'm at GVIS. I'm 44 years old, and I live in Ireland, a bit south of Dublin, at the Irish coast. I've been a Linux sysadmin since 1993 and worked as an IT trainer, as an IT manager, and in 2010 I started another company called Freistyle IT. And we are specialized in building high-performance Linux infrastructures, especially our main product, which is called Freistyle Box, which is a platform as a service that's completely optimized and completely managed by us for Drupal and WordPress websites, especially bigger websites that need complex web hosting infrastructure. When I started building our platform, I started with configuration management from day one. We've grown from a single server and to a few hundred servers now. And we started with our first operations server called Ops01, and it ran two services, Nagios and Chef. And from there, we grew to a much bigger infrastructure. And thanks to Chef, we've been able to manage all these servers with all the different services with two system administrators also doing on-call duty. So configuration management, I think, is totally necessary, and it's good to have it from the start, and it's much easier to integrate it if you have it from the start. Certainly every one of you is familiar with Puppet or Chef or Ansible or other configuration management solutions. So I think it's quite easy to say what's the advantage of using configuration management. You have much less manual changes. In the best case, you don't have any manual changes. And you do everything controlled by a central instance that makes sure that all your servers are configured as you want them to be. Everything is consistent, so you don't have any side effects of configurations that deviate from your standards, and you have a single source of truth. In the case of Chef, you have a central database that contains all the nodes you are running and all the data about these nodes. You can query this database, and you can see, okay, what server is in what cluster, and with this information, for example, you can configure a load balancer. If you add another server, Chef will make sure this server will be added to the cluster. And configuration management also makes sure that you don't have to repeat yourself. You simply get a cookbook or a manifest and use that to have the same installation on every server. But configuration management also has its weaknesses. Mostly configuration management works with periodic convergence runs. So you have, for example, a Chef client that runs every half hour, or in our case, every 10 minutes. And this introduces change lag. It can take up to 10 minutes or half an hour or an hour until changes have been reflected on your servers. And if you depend on information in the central database, this can be even more because first a node needs to do a convergence run. The results of this run are then stored in the database, and then maybe after another half an hour, another node queries this database and uses the updated data. So change lag will be there. This is bad if you have processes that depend on quick changes. For example, cluster membership. You don't want to add a server to your infrastructure and then after half an hour or even later, it actually joins the cluster. Even worse is in the case of master or leader elections. If you have multiple databases that need to work out who is the master, who is the slave, you don't want to have a lot of lag in there. Also, for example, if you are using configuration management services to deploy applications, you want to have that quite quickly. For example, in an early generation of our hosting platform, we had the deployment of the websites controlled by a cron job that ran every 2 minutes, checking if there was a new revision in the Git repository and eventually rolling this out. We had a lot of support requests with impatient customers that didn't want to wait 2 minutes for each of their changes, even with only 2 minutes. So things like deployment or, as another example, service discovery, you don't want to have change lag with that. So when I'm talking about orchestration, I mean that I want to have changes being performed quickly, in the best case, instantly. And I also want to be able to handle failure. For example, if nodes fail, I want this reflected in the load balancer configuration. I want this maybe reflected in deployment services and other things. Quickly means without lag. In the best case, immediate reaction to changes. And I'd also want to tolerate network partitions. Another problem with a central database is if this database isn't reachable anymore for a certain number of nodes, this will also cause problems. For example, if a deployment change needs to be rolled out and one of 3 nodes can't reach the database, we'll have different rollouts on the cluster nodes, and we don't want to have that. In order to solve this problem, I researched a number of tools, and I've taken 2 of them to talk about today. And the first one is Surf. Surf is a quite young tool that's been developed by HashiCorp, which is the company of Mitchell Hashimoto, the author of Vagrant. And it's a cluster communication tool that's very easy to install. It's a simple binary. It's written in the Go language. And you can download a simple zip file that only contains the binary for your Linux platform. You unzip that, put it in user local bin, and you can use it. Go uses the Gossip protocol, which is a peer-to-peer protocol that doesn't need any central data store, like, for example, mCollective, which needs a central message broker to communicate. With Surf, you have each node communicating with the other nodes, exchanging data, so they pass on messages from node to node, which actually goes quite quickly, even if you have a lot of nodes. And the Gossip protocol makes sure that your information within the cluster is eventually consistent. So if you have, for example, a network partition, Surf makes sure that events are communicated to nodes that are temporarily offline. After installing Surf, you can start building your Surf cluster, which is quite easy. I'll also demonstrate that with a virtual machine soon. You simply start your first Surf agent. Is that readable at the back of the room? Not so good. Okay. Well, let's switch to the terminal then. That should be better. So if you've installed Surf, you simply use the Surf agent command to start your first Surf node. You need to give this node a name. Creative as I am, I simply choose node 1. Then I say bind it to the host name and the IP address as RV1. And, well, for a start, that's it. Surf starts, binds itself to port 7946. And as you can see, there was a first member join event for the node itself. And then we can simply start another node. Surf agent node 2. Bind to Surf 2. Now these are still separate clusters, if you can call them clusters. These two servers don't know anything about the other. So what we need to do is now join the second server with the first server. And as you can see up there, the server recognizes that node 2 joined the cluster, and now we have a 2-node cluster, which we can also see with the serve members command. It's that easy. You can do that literally within 3 minutes if you are quick with unzip and quick with typing. You can start your first serve cluster within 3 minutes. Okay. Back here, so that's node 1, node 2. There are several things that Surf takes care of. First is membership. As you saw in the log, node 1 noticed when node 2 joined the cluster, and with commands like serve members, or of course with an API call, you can query which nodes are in the cluster. And so you can use this information, for example, to configure services like, for example, a load balancer. This only works if you also have failure detection. Surf detects failure very quickly. We can test that as well. I'll simply use my VirtualBox console to pause, to suspend the second node, which I'm doing now. It's paused. And there's the member failed event. And now, if I had more cluster nodes, they would be passing this information around. So within seconds, all the cluster members know that node 2 has failed. And if I unsuspend this virtual machine, it goes even more quickly. We are right back. What makes Surf quite powerful is that it also can execute handler scripts for every event that occurs within the cluster. These are the 7 types of events we can have with Surf. So we have the join event, we have the leave event that happens if you, for example, simply stop the Surf daemon on a node. We have the member failed event that we saw earlier. There's the member update event. The member reap event happens if a node has failed for a longer time and the timeout that's configured for the cluster has expired. Then the node is completely taken out of the cluster and yeah, it's gone. And there are two additional events that you can use for your own purposes and applications, which is the user event. You can simply send a user event to notify your cluster nodes of something. And there's the query event where you can ask your cluster nodes to give you a certain information. For example, you can use user events to trigger a deployment. You can say, okay, my Git repository has received another push, and then you'll simply send a user event, deploy my application. All the cluster nodes receive the event, and if they feel like it, they'll deploy your new revision. You can also perform a convergence run. So although there are examples on the SERV documentation that show how you can use an event handler to directly change a load balancer configuration if, for example, a node fails, I don't think that's a good way to approach this, because sooner or later you'll be reprogramming all the functionality we also already have in Puppet or Chef. For example, having templates to generate configuration files, to restart services, things like that. There are proven applications for that, and I don't think I'll replace our Chef server anytime soon. But Surf is quite handy to simply trigger a convergence run, and we'll probably use that to have longer periods between our regular convergence runs. For example, run Chef not only every 10 minutes, but every hour or so. And if need arises, we can simply do a user event that'll trigger a Chef client run as at any time we need it to run. And as I already mentioned, you can use the query event to query information from the cluster. So you can, for example, ask all your cluster nodes which revision is deployed on your local installation, and you'll get all the results back. Okay, so Surf was easy to install, easy to start, and it's very easy to use event handlers. That's, for example, a very simple event handler, a simple shell script that is run every time our Surf cluster receives an event, and it simply uses the environment variable Surf event to see what kind of event that was. And if it's the type user, there's another variable called Surf user event that then contains the name you used for your user event. So calling a user event could look like this. Simply Surf event deploy app. Deploy app is the name you choose for your event. And you'll get a log entry like this, simply received event, user event, deploy app. You can also add a payload. For example, you can say Surf event deploy app and then the git commit ID to make sure the right revision is deployed. Unfortunately, there are limits to that payload. Since Surf uses UDP, you are limited by the UDP packet size, so you can't go wild with your payloads. But if you simply can transfer a kind of key that the client then can use to get more information, I think you'll be good. So let's see how that works. Yes? What happens if I send an event and one of my nodes is offline at that time? As I said, serve, or the gossip protocol to be exact, is eventually consistent. So your failed node will get this message after it returns to the cluster. It may be after a few seconds, a few minutes, or hours. That depends on how quickly your node comes back, but it'll receive the message. Yep, it'll receive it only once. Another question? Is serve limited to a single subnet? No, it isn't. So there's no broadcasting or things like that. You can use also, your cluster can be all over the place. Okay, user events. Using an event handler really is easy. I'll stop my serve agent here and simply say use my handler.sh as an event handler. Serve simply uses standard in and standard out to pass information, for example, about the payload that came with the user event. In order to display what data this is, I'll set the log level to debug. Huh, okay. Never do live demos. Or try to save keystrokes. So even the simple member join event from the node itself triggers the shell script, and the shell script says new event member join. And the data, the payload of this event contains the node name and its IP address. And if I send an event, for example, serve event deploy the damn thing and a git hash like 07fg and so on. Yeah, I haven't joined it with the cluster again. Should do that. So serve join serve2 should do the trick. Okay, I'll have to resend the event because the node wasn't failed, but it wasn't simply a member of the cluster at that time. And now I have my user event with the payload 07fg. It's as simple as that, and of course you can make the things more complex using other programming languages or whatever you like. Another question? That's right. Oh, sorry. So the question is, what nodes do execute their event handler if an event occurs? Is there some kind of master? Can I limit where event handlers will be fired? Event handlers will only be fired for where you've started serve with the event handler information in the command line. And from then on, it's simply your choice how you parse the event, and you can always decide to drop the event in your event handler. For example, if you have different applications that you want to deploy, you can decide on the local machine, is that an application that I even can deploy? And then you can simply drop the event if it doesn't make sense to execute the event. Yes?
Is there a master?
Is there a master? No, there isn't. There are serve nodes that can have certain roles. For example, you can start a monitor agent that will list more information about what's happening in your cluster, but there isn't a single master server. As you saw in my first example, I had serve2 join serve1, and now I did add serve1 to serve2, so there's no master or slave concept here. Yes?
Is that a directed description?
No, it isn't.
So if I grow the number of nodes, I get a likely number of integrants on everything connects there?
Yes, you do. I don't know if it's a frightening number because every node tries to communicate with every other node. The gossip protocol seems to be quite intelligent in terms of bigger clusters, so I don't think that you'll have a problem with running 100 or 1,000 nodes with this protocol. It seems to be quite efficient. I haven't run it on big clusters with a few hundred nodes yet, but I'm quite optimistic that I won't have any problems. Is there any kind of authentication? No, there isn't. You have to have additional measures, for example, control who can access your serve port. Okay, that's serve. I don't know. I don't know actually. I'd have to see the gossip documentation how it'll work internally. Okay. Another tool you can use to have a distributed architecture that is on one hand quite quick in reaction to changes, and on the other hand easy to use, and on the third hand tolerant to network partitions and things like that, is etcd. etcd is a highly available key value store comparable to, for example, Zookeeper or Doozer. It's developed by Core OS and also written in Go. Seems to be all the rage at this time. It uses the Raft consensus algorithm to have consistent data within an etcd cluster, and uses a purely HTTP API to communicate. This makes it also very easy to install. Again, you simply clone the etcd repository, run the build script. You'll also have to have a recent version of Go installed, and then you get a single binary that you can run. Key value store means that you have a hierarchical structure of keys to who you can assign values. For example, here I have a key release that has a kind of hash assigned, and then there's a directory cluster which contains two keys, node 1 and node 2, with their values. So it's easy to use etcd to store information, for example, about new releases to deploy, or to have cluster members listed here. And with etcd, you can run as many etcd nodes as you want. For example, I've taken 5 nodes here, and they use a quorum algorithm to make sure you still keep consistent information even if some nodes fail. So if you have 5 nodes, of course your cluster is available. and your cluster will stay available as long as it has more than half of the original nodes. So with one node failed, it's still available. With another node failed, it's still available. And if your servers are contacting etcd to get information, well, if they ask one of these three, they'll get the right information because they are in the majority. If they ask one of the, or if they try to ask one of the failed nodes, or if these nodes are in another network partition, if you have some kind of network problems, these two nodes will refuse to make changes to the key value store. They'll still be able to read keys, but in order to preserve consistency, these separated nodes will not make any changes anymore. And if your cluster shrinks to 2 nodes, of course, it'll be unavailable. So what number of nodes would be good? Well, obviously, to have a efficient quorum result, you will probably want to have an odd number of nodes. And you can start with 3 nodes. And according to CoreOS, they recommend having at the most 9 nodes. Otherwise, communication between the nodes will be hit by a performance malus. So 3, 5, 7, or 9 nodes would be good numbers. Writing to the key value store is easy. You can use the etcd control command line tool, or you can simply use HTTP requests using curl, or of course you can always use an application to do these HTTP requests, and you can say, for example here, set the key message to the value hello, and etcd will do that. And if you use the curl call here to set the same key to the value test, you'll get back a JSON payload that'll tell you, okay, I've set the value to test, and you'll even get information about the previous state of the node. Because, so it says, okay, previously the node had the value hello. Reading this key value store is equally easy. etcd control get, or a simple get request via HTTP will get you your information. And using the delete method, you can also remove keys. Do you get the previous value as well? No, you don't. You may be able to use the modified index to get previous values. I'll get back to the modified index soon. So that's all good, but in terms of automating infrastructure, you'll probably want to know when keys change. For example, if another node joins your list of cluster nodes, or if the release key changes after a git push, you'll want to know about that, and that's where you can use the watch, which will simply wait until a key changes, or you can use also a recursive option to say, I want to watch the cluster directory and want to be notified if any entry, any key within that directory changes. So for example, you can use this curl request to say, okay, watch the release key and wait until it changes. It'll do a long-running HTTP call that will be kept until the event happens, and as soon as it happens, you'll get another JSON payload that contains the key and also the previous state of the key. To come back to a previous question, what happens if my web server, for example, was offline for some time and couldn't watch my release key? How will it see if there was a change? There's another option you can use using the wait index option. And there you can say, okay, the last state I know of this key, for example, is the index 14. So if you do the same watch with wait index equals 14, you'll get your JSON payload back immediately because your wait index is lower than the current index. So etcd will give you your information immediately, and you'll see that you need to catch up. You can use etcd for quite a number of applications. Building upon the watch concept, you can use, for example, locking. Your application can say, okay, I'd like to change this key, and I'd like to own it so that no one else can change it anymore. If you're the first, you'll get the change and you'll get the lock. And if another node comes and says, okay, I'd like to own this key, etcd will say, okay, it's already taken, you need to wait. And not until the first server gives up its lock, the second server will get its lock. You can use this, for example, for leader election. If you have different database masters that need to find out who will be the master and who will be the slave, you can use that. You can use it to assign failover IP addresses. Every time you need to decide who is going to be it, you can use this. And I also have an example for that, this leader election. So let's say we have our etcd cluster, here the green circle, and our application. And our application wants to know what database to talk to. So it'll ask the etcd server, what's my database? And etcd will say, don't know. There's no database. And the app now says, okay, I'll wait, which means I'll request a lock on the database master key. And as soon as that changes, it'll get back the information. This only will change if we get a database. So let's say we get our database. The database then goes to etcd and says, I'd like to be the master. And of course, it'll get this granted. Now etcd this, of course, will also be done with a locking approach. So the database X will request a lock on the master key. It'll get it, and etcd will then use the already established connection to your application to say, talk to database X. And database X now will also have its lock on the master key, and your app can now work with database X. Okay, applications running, time to set up a standby database. So we have database Y, which will also come and say, I'd like to be the master. But no can do. There's already a master, and there can be only one. So database Y will now also try to get a lock on the master key, but it'll have to wait. wait until database X fails, which will sever the connection to your application, which will also have etcd realize database X has gone. So the lock of database X will be gone also, which will enable etcd to give the lock to database Y. And it'll also inform the application that the database Y is now the master. Application can talk to the database, and that's it. These are only two examples of current technology that enables you to add more dynamic to your configuration management. There are more technologies. For example, I mentioned Zookeeper or Doozer as key value stores. There's also cluster management tools similar to Surf, for example, mCollective, or a list of other tools. But in my opinion, Surf and etcd are both very, very simple to set up and to use. So it's easy to get started. For example, simply with the use case of using Surf to trigger additional conversions runs with your existing configuration management solution. And from there, you can go wherever you want. You can add deployment functionality. You can make your event handlers as complex as you want. And it's very easy to grow your infrastructure and without introducing a lot of lag, without losing the possibility of having changes made very quickly. For example, to remove cluster nodes as soon as they fail, to add nodes in a auto-scaling environment, for example, and with tools like etcd, it's also quite easy to have a central, no, it's not central, but a very highly available key value store that can contain a lot of information. etcd performs perfectly with hundreds or thousands of changes per second. So even if you have a very dynamic environment, etcd will serve you well. Okay. That's my presentation so far. If you have any questions, I'm available here. You can find slides of this talk and other talks at Speaker Deck. You can reach me on Twitter or via email, and I'm looking forward to your questions.
What are the advantages over Zookeeper? Because from what I've seen in your presentation, it looks pretty similar from the concept. Mm-hmm. And Zookeeper itself, it's complex, yes, but it is very mature. It just works.
That would have been my answer as well. Zookeeper, for example, is more complex to set up. It'll also require additional libraries. For example, if you want to integrate it in your application, you'll always need the Zookeeper library that fits your programming language. And that's one of the main advantages of etcd. Since it simply uses HTTP requests, it's very easy to use, and you are not dependent on third-party libraries, which can be quite complicated from time to time with Zookeeper, getting the right, for example, Ruby gem to use and have choose a well-maintained one and things like that. Also, Zookeeper seems to need a lot more connections if you are using things like watches or stuff like that. From what I've read, etcd is far more efficient in terms of network connections to propagate information within the key value cluster or with the clients that are depending on it.
Okay, thank you.
Further questions?
Just an additional cool tool to use with etcd is Helix DNS, which points, or you point a host name and you give a value as an IP address, and from then on you can query this DNS and it will serve you the host name with IP address. So it's pretty cool.
So you can use etcd as a DNS server,
you
basically.
set host name equals IP address, and from then on you can use it as a DNS entry.
That's interesting. Of course, you can use tools like Serve or etcd to have a highly responsive DNS server. So, for example, if you use TinyDNS, you can make changes to your DNS information if a node fails or things like that quite quickly. But using etcd directly as a DNS server is very funny. Yeah.
Do we have any questions left?
I'm sorry, it's a little late today. I did not understand what can I use this etcd for if I can only use it on 3 to 9 unequal nodes. What happens with scaling? What are the use cases for such a tool? I really did not understand.
Okay. In that case, we have a well, let's say client-server environment, or it's a client etcd cluster environment. You can have as many clients as you want, but to be highly available, your etcd you can't run a single etcd server. You need an etcd cluster, and for that you'll use 3, 5, 7, or 9 nodes. 5 nodes seems to be quite common because you will have a lot of high availability. You can lose as much as 2 nodes without the cluster getting unavailable, and that's the limitation. Of course, you can have hundreds or thousands of clients writing to or reading from the etcd cluster. Back there.
One question I have, if you have 5 nodes and one is gone and you decide that it's gone for good, could you remove it from the cluster, or will it stick with the cluster as long as it comes back? So you have 5 nodes, one is missing and then another one is missing, and then you want to say, okay, my new cluster size is 3. So if you grow to 5 nodes, could you reduce the size of the nodes, or could you just add servers to the etcd cluster?
I'm not sure. You'll certainly be able to solve that problem with a restart, of course, but you probably don't want to do that. I remember reading about recent versions having additional options regarding the cluster nodes. You can do HTTP requests to etcd also to, for example, get a list of all the nodes. And there may be a new function that enables you to remove a node from the cluster membership list. But I'm not sure about that. I need to research that. I just remembered another hint. Starting an etcd cluster is quite easy. You start your first node, and then you start your second node, and simply add a command line option that says join the cluster of server 1, for example. So you'll simply say which are the other nodes in your cluster. But that requires you to have at least one cluster node, to know at least one cluster node, and you'll get into a bootstrapping problem. There's the possibility of running a discovery cluster, and the folks from Core OS run such a cluster. You simply use an individual token, and you say, okay, here's a cluster node that wants to join my etcd cluster, and you'll register basically each node with this discovery service, and you can get the other nodes back from this discovery service without having to know what nodes you have. So there's the discovery.etcd.io, I think, which you can use to simply. So, for example, you can use a simple Puppet manifest that simply says, okay, you are a etcd node, ask the discovery service for the other nodes, if there are any, and you can do the same on all the other nodes, so your nodes don't need to know of each other initially with this discovery service. Yes?
One more question to serve. It looks promising, but isn't there some feature request to have a cluster secret like in CoroSync? Because from the concept it looks like CoroSync, but for us CoroSync does not scale. So if it scales but doesn't have a cluster secret, yeah, I would not put this into production.
Yeah. I'm not aware if there is some kind of request for authentication, but I'll find out for you. Simply ask me again in a few minutes.
Any further questions? Okay then, thank you very much, Jochen.
Thanks for staying awake.